A planet almost identical to Earth got tossed aside by a computer. It wasn't a meteor that wiped it out, nor was it a star exploding. NASA's algorithm, a program built by humans to sift through cosmic data, looked at that planet's signal and decided, noise. Sensor error, not worth a second glance. The file vanished into a digital archive of discarded data, destined to sit there forever. And it would have, if not for one unexpected twist, which we'll get to shortly. But first, we need to ask, why did humans build a $600 million telescope and send it beyond Earth's atmosphere at all? Why search for a new home billions of kilometers away when an entire solar system lies right next door? Here's why. Our neighbors are, to put it mildly, far from welcoming. Mars averages about minus 60 degrees Celsius. Its atmosphere is thinner than a plastic bag compared to Earth's, made almost entirely of carbon dioxide. Jupiter doesn't even have a solid surface. It's a massive ball of gas where winds roar up to 300 miles per hour. Venus faces surface pressure 90 times greater than Earth's, with temperatures hot enough to melt lead. Not a single planet in our solar system offers conditions where a person could step outside without a spacesuit and survive. To colonize any of them means building airtight habitats, essentially spacecraft resting on solid ground. It's not moving to a new home. It's a lifelong sentence inside a capsule. And here, science makes a crucial pivot. If no planet nearby can support life, we have to look farther, beyond our solar system. We search for exoplanets, worlds orbiting other stars, worlds that might hold liquid water, breathable atmospheres, and temperatures where protein-based life can survive without freezing or breaking down. But how do you find a planet tens of light years away that doesn't shine on its own? A planet is just a tiny speck next to a blinding star. It's like trying to spot a moth fluttering near a lighthouse beam from across an entire ocean. On March 7, 2009, a Delta II rocket launched from Cape Canaveral. On board was NASA's Kepler Space Telescope. Its sole mission, to hunt for exoplanets. More precisely, small worlds that resemble Earth, orbiting their stars at just the right distance, not too close, not too far. Kepler uses the transit method. It watches a star's brightness non-stop. When a planet crosses in front of the star, the brightness dips by a tiny fraction, like a mosquito fluttering past a car's headlight. That faint flicker is enough to signal something is there, but to confirm it, you need several of these transits, which means watching the same star for months, sometimes years. Kepler focused on one small patch of sky, a region in the constellation Cygnus. Not the entire night sky, just a tightly confined square about the size of a fist held at arm's length. Inside that fist-sized patch, there were 190,000 stars, each one a potential host to a planetary system. Every star needed constant monitoring. Scientists recorded the slightest flickers in brightness. In other words, 190,000 light curves ticking away simultaneously, 24 hours a day, 365 days a year. And this went on for nearly a decade, until October 2018, when the telescope ran out of fuel. No human could possibly sift through such an enormous amount of data by hand, so they handed the job over to automation, a smart algorithm that decided on its own which flickers looked like planets and which were just noise. The machine worked brilliantly. Thousands of confirmed exoplanets, a triumph of engineering and programming. But here's the intriguing part. Kepler's archives hold a vast number of signals that the algorithm dismissed as false positives. Hundreds of thousands of files tagged with a single word, rejected. And among those files, quietly resting in the digital trash, was a signal from a world that would turn out to be one of the most Earth-like objects ever discovered by humanity. To understand how it ended up there, and why the machine got it wrong, we need to dive into how the algorithm sifted through those endless streams of light. We need to find where exactly the line was drawn between discovery and discard. The boundary boiled down to a single line of code. NASA's algorithm, known as RoboVet, scrutinized every dip in brightness and delivered a verdict: planet or noise. No maybe, no needs further review, just a binary yes or no. And in the vast majority of cases, it got the answer right. RoboVet confirmed thousands of exoplanets. It worked faster than any team of astronomers, more accurately than any bleary-eyed intern running on too little sleep. It earned trust, and for good reason. But every filter has its blind spot. The algorithm caught signals that looked textbook perfect, smooth, periodic dimming with sharp edges. Yet when a signal strayed even slightly, more noise, a less tidy curve, RoboVet tossed it into the folder marked false positive. Not labeled uncertain, not queued for a second look, straight into the digital trash. Neat. Final. Here's where it doesn't add up. We build a $600 million telescope. We launch it into orbit. We spend 9.5 years gathering data. Then we hand the sorting over to a program that literally can't doubt its own decisions. It's like hiring an archivist who works flawlessly fast, but throws away every document with a bent corner without reading it. By 2020, Andrew Vanderberg, an astronomer at the University of Texas at Austin, assembles a small team. Their idea is simple and wildly ambitious: to manually review what the robot had discarded. Not everything, of course. There's no way to sift through hundreds of thousands of rejected signals, but a significant portion. Vanderberg knew the algorithm made mistakes, not often, but consistently. Every false negative meant a potential lost world, one that no one would ever see because the machine had made the call for everyone. The team was working with what was essentially archival junk from NASA, files that no astronomer had opened since they were automatically sorted, brightness charts marked as defective, and somewhere among those charts was a single data set from a star about 300 light-years away, a red dwarf, dim and unremarkable. The automated system labeled its transit signal, that regular flicker, as a false positive, a mistake, just noise. Or rather, not noise. When Vanderberg and his colleagues unfolded the light curve and overlaid the periods, it became clear. The dimming repeated, every 19.5 days, consistently. Something was passing in front of that star, something almost exactly Earth-sized. The algorithm was wrong. And in the trash bin lay a planet that would turn out to be one of the closest matches to our own ever discovered. The discovery of Kepler 1649c came because a group of people refused to accept the machine's verdict as final. NASA's program had automatically flagged the signal as a false positive. Only a manual reanalysis brought it back from oblivion. Without Vanderberg's initiative, this world would have remained just a rejected line in a database. Forever. Now, having pulled this planet out of digital darkness, researchers could finally examine its details. What they saw in the data left them speechless for a few seconds, until someone spoke the number that changed everything. 1.06. That's the number that left the team speechless. The radius of Kepler 1649c turned out to be just 1.06 times the radius of Earth. That's not just a difference, it's within the margin of error. Put two spheres side by side, and your eye won't tell them apart. 300 light-years away, orbiting a dim, red dwarf star, yet almost an exact twin of our planet in size. But size is only the beginning. This planet receives about 75% of the energy Earth gets from the Sun. To put that in perspective, it's the difference between a July afternoon and an April morning. Cooler, but still enough to keep water liquid. At the time of discovery, no other exoplanet matched Earth so closely in these two crucial ways: size and the amount of heat it receives. And here comes a question that twists our instincts. Kepler 1649c orbits its star once every 19.5 Earth days. A year there is shorter than most vacations. Its orbit is so tight that if you placed it in our solar system, the planet would sit well inside Mercury's path, the closest planet to the Sun. Mercury's surface temperature reaches a scorching 430 degrees Fahrenheit on the day side. You'd expect a planet that close to its star to be baked and barren, but the opposite is true. Red dwarf stars burn much cooler and dimmer than our Sun. They're so faint that their habitable zones, the regions where temperatures allow liquid water to survive, hug right up against the star. What would be a zone of instant evaporation around our sun turns into a cozy, warm spot around a red dwarf. Kepler 1649c sits exactly in that zone. The right temperature, the right size, and theoretically, liquid water could exist there. It sounds almost perfect, but red dwarf stars have a habit that spoils the whole picture. These stars are unstable. Their magnetic fields are chaotic and unpredictable. Every now and then, a red dwarf unleashes powerful flares, bursts of ultraviolet light and charged particles that sweep over everything nearby in minutes. For a planet hanging close to such a star, each flare is like someone repeatedly opening the door of a microwave oven with a sandwich inside. Only in this case, the sandwich is the atmosphere. The ultraviolet radiation strips molecules from the upper layers of the gas envelope, while charged particles break chemical bonds. With every flare, the atmosphere grows a little thinner. A billion years of these flares, and the gas envelope might vanish entirely. A bare rock under a crimson sky. This is the biggest obstacle to life near red dwarfs. Not temperature, not size, radiation. And here, everything hits a wall. A wall that, at the time of discovery, was impossible to break through. If Kepler 1649c has a dense enough atmosphere, say one with a strong magnetic field or the right chemical makeup, it could withstand these impacts. It could deflect particles, recover, hold pressure. But if it has no atmosphere, or if it's too thin, the surface has long since been sterilized. We still haven't studied the composition of this planet's gas envelope. We literally don't know if there's air there at all. Without that answer, all the similarities to Earth, size, temperature, position in the habitable zone, remain just a set of promising numbers on paper, nothing more. The size is perfect, the energy is just right, but to understand whether this world is alive or dead, we have to see something no telescope up to that point could ever detect. A razor-thin layer of gas, 300 light-years away. And for that, science needed a completely different kind of instrument. On December 25, 2021, a rocket launched from the Kourou spaceport in French Guiana carrying a payload decades in the making, the James Webb Space Telescope. 6.5 tons of golden mirrors, heat shields, and infrared optics, set off for a spot 1.5 million kilometers from Earth. There, with the sun, Earth, and moon behind it, only darkness and alien light lie ahead. The Hubble telescope glimpsed distant worlds. Kepler measured their shadows. But neither could do one crucial thing: read the air of an alien planet. Webb can. When an exoplanet passes between its star and the telescope, a tiny fraction of starlight filters through its atmosphere. Every molecule in that thin layer absorbs light at a precise wavelength, leaving a fingerprint, like a mark on glass. Webb can catch those fingerprints and decode them. In simple terms, it can tell us what the air of a planet hundreds of light years away is made of. But how exactly does it work? 3 key instruments operate on board, each handling a vital part of the mission. The near-infrared camera, known as NIRCam, acts as the telescope's main eye. It captures the faintest light signals from distant objects, so dim that the Hubble simply couldn't detect them. NIRCam spots the planet. Then, the spectrograph called NIRSpec takes over. It breaks light down into a spectrum, like how a glass prism splits white light into a rainbow, but with the precision to identify individual molecules. Carbon dioxide leaves a dip at one wavelength, methane at another, and water vapor at a third. Each gas has its own unique signature, like a barcode on a package. NIRSpec reads those barcodes. The third instrument, MIRI, works in the mid-infrared range and reveals what's invisible to the naked eye: heat radiation, cold clouds, weather systems, temperature patterns across the planet's surface. They all show up in MIRI's thermal readings. 3 instruments, 3 layers of information. Now the question is, where should we point this optics first? The answer came from the past. Back in 2019, the trusty old Hubble zeroed in on a star called K218, a cool red dwarf in the constellation Leo, 120 light-years from Earth. Orbiting that star was a planet designated K218b. Hubble caught the first hints of water vapor in its atmosphere, but the resolution wasn't sharp enough. The image was blurry, the data barely above the noise. Still, that alone was enough to mark this planet with a red flag for future telescopes. Hubble passed the baton, Webb took it up. Here's what scientists found when they took a closer look. K2-18b doesn't resemble Earth or Neptune. It's over 8.5 times more massive than our planet, with a size somewhere between Earth and the ice giants. Astronomers call planets like this sub-Neptunes, and there isn't a single counterpart in our solar system, not one. But here's the strange part. This planet orbits within the habitable zone of its star, at just the right distance for liquid water to exist. A planet nearly 9 times heavier than Earth, and yet it might still support life? Here, a new category takes shape. Astronomers at Cambridge coined the term Hycean worlds, a blend of hydrogen and ocean. These are planets entirely covered by a global ocean beneath a thick hydrogen atmosphere. Not a rocky Earth with a thin gas layer. Not a gas giant without a surface. Something else. A water world with an alien sky. And K2-18b became the flagship example. Before this idea, we searched for life on planets as close to Earth as possible. Same size, similar atmosphere, familiar rock types. Hycean worlds shattered that framework. Suddenly, the range for finding life could be far broader than anyone imagined just 10 years ago. Turning its golden mirrors toward this watery world, the Webb Space Telescope began to break down its light into spectra. What appeared on the scientists' graphs exceeded their wildest expectations. The first thing that stood out in the spectrograms was methane. Then came carbon dioxide. Alone, these gases don't prove much, but together, in the right balance within one atmosphere, they tell a story you want to keep unraveling. The James Webb Space Telescope split the light passing through the gas envelope of K2-18b and found clear signs of carbon-based molecules. Not just traces or hints, distinct dips in the spectrum at wavelengths where methane and carbon dioxide absorb infrared radiation. This marks the first time such a combination has been detected in the atmosphere of a planet located in the habitable zone. But the data revealed something else, or rather, something that wasn't there. The spectrum showed no ammonia, and that absence spoke louder than any presence ever could. Ammonia is a common ingredient in the atmospheres of gas giants. Jupiter is saturated with it. So is Saturn. If K2-18b were just a bloated ball of gas, ammonia would be there too. But it isn't. That means hydrogen in the atmosphere interacts with something that breaks down or absorbs ammonia. Something liquid. Something massive. A global ocean stretching from horizon to horizon is the only explanation that fits all the data at once. Methane and carbon dioxide are present. Ammonia is absent. A hydrogen atmosphere? Yes. An ocean beneath it? Almost certainly. Every observation comes from different sources, yet they all point to one conclusion. We're looking at a Hycean world, a water planet with an alien sky. And here lies the biggest mystery. Methane. Where does it come from? About 90% of the methane in Earth's atmosphere comes from biological sources. Cows, swamps, rice paddies, methane-producing bacteria at the ocean floor. They all contribute. But the remaining 10%? That's geology. Volcanoes, hydrothermal vents, and chemical reactions between water and rocks deep underground. Methane can form without a single living cell. Just heat water, add olivine, and wait a few thousand years. So methane alone isn't a verdict or proof. It's like a boot print on a wet trail. Someone walked here, but was it a person? Or just a fallen branch landing the right way? It's unclear. You need a second clue. One that geology simply can't explain. And the James Webb Space Telescope might have found it. In the spectrum of K2-18b, scientists detected a faint signal, barely at the edge of what their instruments can resolve, but unmistakably there: dimethyl sulfide. This volatile sulfur compound on Earth is produced by only one process: phytoplankton. Tiny algae drifting through the upper ocean layers. They release millions of tons of dimethyl sulfide into our atmosphere every year. No known geological process can generate this molecule in any significant amount. On our planet, Dimethyl sulfide is the scent of the sea, that salty, iodine-tinged taste of air along the coast, and it comes exclusively from living organisms. This signal still needs confirmation. Follow-up observations, cross-checks, independent teams all lie ahead. But if it holds up, humanity will face a milestone 4 centuries in the making, ever since the invention of the telescope. Chemical evidence of biological life beyond Earth. The Webb spectrographs have indeed detected a signature that could upend our understanding of biology in the universe. Whatever the answer turns out to be, it's a difficult truth to face. If the dimethyl sulfide turns out to be just noise, an artifact, then we remain alone in a silent cosmos. But if the signal is real, it means life emerges more easily than we imagined. Either way, the 124 light-years separating us from this cosmic ocean remain a distance we have yet to overcome. 124 light-years. A radio signal sent today toward K218b will reach that planet in 124 years. If someone is there and they decide to respond right away, we won't get their reply until 248 years after we hit send. That's a quarter of a millennium for just one hello and one hello back. When we press send, it will be the year 2025. By the time the answer arrives, it will be the year 3273. No country in human history has lasted that long, and that's just radio waves, the fastest thing we have. Physical travel is a whole different challenge altogether. The Voyager probes, launched back in the 1970s, remain the farthest human-made objects from Earth. They've been traveling for almost 50 years now. It would take them several thousand years to reach the nearest star systems. Not decades, thousands of years. And keep in mind, K218b is not even close to the nearest star. It's about 30 times farther than Proxima Centauri. Imagine we build a spaceship of the future. Not one from today, but the kind engineers dream about in their most optimistic papers, capable of reaching 10% of the speed of light. That's 30,000 kilometers per second. You could travel from New York to Los Angeles in a quarter of a second. Even at that speed, this ship would take about 1,240 years to reach the ocean of K218b. To put that in perspective, 1,240 years ago, written language didn't even exist in Russia. Here we find a principle worth remembering, not just for space exploration. Knowing where the treasure lies and actually being able to reach it are two completely different skills. We have mastered the first. The second, a total failure. There is, however, a glimmer of hope. Yuri Milner's project aims to develop nanoprobes, tiny devices the size of a postage stamp, propelled by laser beams to speeds close to the speed of light. The current target is more modest, Proxima Centauri, about 4 light-years away. We have a video about this star, please check it out. But even if this technology works, reaching K218b means more than 100 years of travel, and a probe the size of a stamp won't land on the ocean's surface. It will fly right past, snap a few photos, then send them back, where they won't arrive until 124 years after the flyby. The limits of our solar system, the scarcity of liquid water, the thin atmospheres, the deadly radiation, we talked about at the very start. But now, a barrier of a completely different kind stands in our way. A prison of interstellar distances. We've found the door. We've seen what lies beyond it. But the key doesn't fit. And here's what's truly strange. This knowledge, the unreachable ocean over 124 light-years away, didn't change space. It changed us. From the hunt for exoplanets, astrobiology was born. A whole science dedicated to life we have yet to find. A new genre of science fiction about watery worlds took shape. And with it came a realization that never existed before. Earth isn't just a launch pad. Earth is the only home we can be absolutely sure we have. Dimethyl sulfide in the atmosphere of a distant planet still awaits confirmation. The Webb telescope keeps watching. Data is piling up. The answer, whether it will be yes or no, is racing toward us at the speed of light. crossing that very same 124 years of empty space. While it travels, we have time to look down at the one ocean whose scent we know for certain.